So energy is the ability to do work, but we defined work as the dot product of force and distance. And when we did that dot product, we kind of did our diagram that showed that this would be my force times my distance, and we lost our vector characteristics. So we were able to work the problems without looking at our vector characteristics. We also talked about that we have conservation of energy. And that's what we're going to use this diagram to look at. And remember, we also have conservative energies and our non-conservative energies. And these were things like losses due to friction, or drag. And this is because Mother Nature isn't fair. And this gets back to the second law of thermodynamics. So we're going to look at our roller coaster here. So we've got our roller coaster here. And so if I do work, and let's say I've done 100 joules of work, and now I'm looking at my little roller coaster car up at the top, we know that the work to get to the top is going to equal our total energy at the top. And that's coming from our conservation of energy, which is now going to be equal to my potential energy due to gravity, which is equal to mgh, which is now going to be equal to my 100 joules. And if we say that this distance is 20 meters, and I'm going to make this distance 10 meters, and I make this distance 15 meters, we know what's going to happen as my roller coaster comes down. Here, I'm going to have the total energy is going to equal my 100 newtons, or my 100 joules, which is equal to the potential energy due to gravity plus kinetic energy due to my kinetic energy that's there. Now, as my roller coaster continues, I'm going to be at this point. Well, guess what? If we're making the assumption that we don't have any of these non-conservative losses due to friction, and we're going to make this assumption that this is a frictionless roller coaster, my total energy is still going to be 100 joules, but it's still going to be equal to the potential energy due to gravity plus my kinetic energy. So we're going to see energy change back and forth. So let's look at this one here. So if my total energy is equal to 100 joules, this is going to be mgh. And then I have my kinetic energy, which is 1/2 mv squared. I need to know what this potential energy is there. Well, if I have 100 joules is equal to my mg times 20, mg is going to equal 50. Oh, it's 5 newtons, sorry. I'm doing my calculations right. 5 times 20 is 100. So that's going to be 5 newtons. So now if I do this part, my mgh, which is now 10, that's going to equal 50 joules. So 100 joules minus 50 joules is equal to 1/2 mv squared. We can find the velocity at this point in the ride, because we now can figure out what the mass is, because the mass is just going to be 5 newtons divided by gravity. We can go ahead and finish off our problem here, and we can find out information about this system. So this gives us a nice, helpful way to look at our systems. Let's take it in a little bit differently. So I'm going to have a bowl here. And I'm going to have an ice cube in my bowl. We're going to have my ice cube has a mass. We're going to give it a 0.1 kilogram mass. We're going to say my bowl here. Oh, let's make it 0.5 meters because we want to demonstrate something. And we can actually measure when we actually have our ice cube on the other side. We want to know the height of our ice cube as it goes over here. Now, if I had no friction, no loss of anything, and I had perfect use of kinetic energy or perfect use of my energy, we know that the ice cube would end up back at the top because I have conservation of energy. But now let's say we lose. Let me see what I want to lose here. I'm going to go ahead and calculate my potential energy just so that I have that set up. So I have 0.1 kilograms times 0.5 meters times 9.81 meters per second squared. I got to get my calculator out. Okay, I got 0.1 times 0.5 times 9.81. This equals 0.49 joules, but I'm going to lose, let's say I'm going to lose 0.2 joules due to heat and friction. Okay, and I want to know the new height that it reached. So I'm going to look at my total energy is going to equal the potential energy of the system minus energy lost. So now I'm going to get 0.49 joules minus 0.2 joules is going to give me 0.29 joules, which is going to give me my new height that I'm trying to solve for. So I'm going to get my 0.29 divided by my 0.1 times my 9.1 meters per second squared. It's going to give me my new height. And that should give me like 0.3 meters. So we can use our conservation of energy to do a variety of things. So let's work another type of problem. let's think of we're going to say that this is 25 degrees. And I've got a spring here. And I'm going to put a marble on the spring. And I'm going to compress my spring. So my new compression. And we talked about, the other day, that force was equal to minus kx, where this is stretch. But this can also be compression. Because if you think about it, if I compress my spring, we know that my compressed spring is going to want to extend out. Oops, I'm drawing pictures that you guys can't see. So we can see our spring, and so it can be stretch or compression. Hooke's law works for both. So I'm going to give a spring constant for this spring. We're going to give our spring constant, let's say 10 Newton meters. We're going to compress our spring let's do 0.25 meters. And we're going to give our marble a mass of 0.25 kilograms. We compress the spring and we're going to let that marble shoot up. So we're going to make the assumption that all the energy from the spring is going to go into the marble. And once we do that, it's like playing pinball. My marble is going to go up. We want to know the distance that our marble travels. So if I go back to our little equation sheet, we know that the potential energy of the spring is going to equal 1/2 kx squared. So we can calculate that. That's going to be 1/2. I said that's 10 Newton meters. And we compressed it by 0.25 meters. And we're going to square that. So I'm going to end up with units of Newton meters, which is going to give me joules. And so now I'm going to go ahead and do that calculation. I'm going to get 5 times 0.25 times 0.25. Gives me 0.3125 joules. But conservation of energy says as long as I'm not getting any dissipation, that's going to equal my potential energy due to gravity, which is going to equal mgh. So I'm going to take my 0.1325 divided by the mass times gravity of my marble. That gives me H. Says that I've gone up 0.127 meters. So what this is saying is there's my triangle up this ramp. And this side is 0.127 meters. I know my angle. And if we make the assumption that this is just starting from our bottom, even though I didn't draw the picture as pretty as I would like to, I'm going to have that sine of my angle is going to equal the distance divided by, sine of my angle is equal to the height divided by the distance. Distance is equal to height divided by the sine of the angle. And now I'm going to get my 0.127 divided by the sine of 25 degrees. There we go. And this gives me 0.3 meters. If I've done all of my punching into the calculator correctly. So we can use that conservation of energy to give us a variety of types of problems that we can play with. So we've done our spring problem, we've done our roller coaster problem, want to do one power problem. So if we do work, so we're going to raise a bucket. And we're going to raise a bucket 10 meters. Our bucket has a weight of 50 newtons. And we're going to do this in a time of 30 seconds. We can calculate the power. And the power is just going to be the work. I get my 50 times my 10. That gives me Newton meters. And I have 30 seconds. And that says that we have 6.7 watts. So power calculations are pretty straightforward, especially once we get those pieces that are together. All righty, folks. I know it's been a long day. I'll stick on for questions, but those are the example problems. Tomorrow we'll start momentum.